Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson, and I think we're talking about confidence bounds.
Confidence bounds, and where do they come from? But, just as I was hitting record, the button next to it on the Zoom agent I'm using or whatever it's called, had an AI companion. And I saw one the other day, Chris, that I'm probably going to get the joke wrong, but it was basically, I think AI is being done backwards. I don't need a AI agent to do poetry and writing for me or, create works of art. So I have time to go out and clean the house. I need an AI agent that will clean the house for me so I can go do poetry and art.
Right. That's actually yeah, cool. I mean, poetry and art, though, I suppose, are more mental, and AI can't pick up a vacuum cleaner and go do the thing. But no, I take your point. Which parts of modern life we're trying to optimize and which parts we're trying to get rid of.
Oh, and I saw a note yesterday that it was somewhere on the order of 2 billion essays have been written by AI for schools kids, high school and college kids. And the article was more about the hesitancy of schools to put in AI detection systems on their writing. But be that as it may, we did get a question the other day, though, Chris. And
was it from a real person or from someone generated by AI?
There were spelling errors, so
real person it is then.
Yeah. Oh no! Don't tell anybody, because then they'll figure out how to put in particular spelling errors. Yeah. Although it'd be hard to judge because I can't tell if it's spelled right or not, one way or the other. But the question was, and it was basically on an article on Ashendo that talked about some confidence bounds for a metric, and it was MTBF metric. So my first response to the person was, well, why are you using MTBF when you use something useful? But we've talked about that before, lots of times. So they came back, though, and they said, well, where's the derivation for that set of bounds? Where does that come from? And I never had thought of that before, because it's stuff I've, found in different reference books and places like that, and it's built in the software nowadays. So I hardly think about it. And I know that you think about stuff like this just for fun, so I thought I'd ask you.
No, I mean, it's really simple, actually. It's and when it comes to like the MTBF and the chi-square distribution, for those of you who aren't aware, probability distributions are essentially little, what's the word I'm looking for? Let's just call them curves. It's not the best term, but a function or a curve which just tells you which random variable value is more likely than another one. And I suppose the most famous probability distribution there is the one that gives rise to that curve, which looks like a bell, the bell curve, which is from the normal distribution.
Or Gaussian.
Gaussian. Yes, that's another one. Or Gaussian distribution. Because Carl Gauss was one of the first ones to actually use it. And again, so people who start doing reliability stuff, even though we advise against using the MTBF, there are still scenarios where good reliability engineers are forced to use the MTBF or forced to verify the MTBF through testing or something similar. But and then you have this weird sort of chi-square distribution, which just appears in textbooks and says, well, this is how you calculate the confidence bounds on the failure rate or the mean.
Yeah. It has weird degrees of freedom. It's like 2R plus 1 or minus 1 or something like that. And depending on if you have a time truncated or event truncated, it has different degrees of freedom. And yet the basic question is, it doesn't matter whether it's for the MTBF or if it's for a Weibull distribution or for whatever. It's like there's formulas all over the place for how to put a confidence bound on something. Even if you just got a collection of numbers, you want to take the have an average and you put a confidence interval on it.
Right.
There's formula after formula after formula for all the different circumstances. And so it was, so I went looking. I found a mill standard, I think 761, that um while it and it was I went to the NIST engineering statistics handbook online. It's a great resource. And it referenced the mill standard that then I went and found, which is way out of date and been discontinued decades and decades ago, but they're free and they're available. And it referenced where the origins of this confidence bound came from for an MTBF on a time truncated event or situation, um, was from a paper in technometrics or something like that, in 1960. So I went looking for that. And his proof or his derivation of it was, well, of course, it's a chi-square distribution with these degrees of freedom. So it went from we have a MTBF in this circumstance, and because it's a Poisson process, or of course it's a chi-squared. And I'm like, I think I missed a piece of that logic there, but
No, it's actually a bit more wide known than that, and I've actually derived it from scratch just for
I
some
knew I was
university
asking the
courses.
right person.
But it all comes down to this concept of likelihood, and we don't want to bore our listeners or make them self-harm when they already do from listening to our podcast. But let's just say you're walking down the street, and you find a discarded shoe. And the size of the shoe, it doesn't say it's a men's shoe or a woman's shoe, but it's size 6.5. Let's just say that.
Okay.
Now, we know that the size of people's feet essentially is a random variable. So if you walk up to and randomly selected a man, the size of their foot size would be a random variable based on your selection. Same with a lady. But we also know that men's feet tend to be bigger. So if there was a curve describing the distribution of men's feet, it would be describing foot sizes which are larger, the 8s, 9s, 10s, 11s.
Mm-hmm.
Whereas if you were to look at women's feet, there would be a distribution where the foot size would be smaller, the 4, 5, 6, and 7s. And so what size shoe did I say? We found a 6.5. Well, from that, if you pick up that shoe and you had no other clue about whether it came from a man or a woman, you would automatically probably say that this is more likely to be a woman's shoe or shoe from a woman because of its size. And that's all likelihood is. You look at, you might observe, for example, 100 things and they all fail within an hour. Then you say, okay, well, the MTBF is likely to be less than an hour for this particular device or MTTF, because they're all failing within an hour. So you can say, okay, a mean time to failure of 2 hours is unlikely. A mean time to failure of 30 minutes, like less than an hour, is more likely than 2 hours. And we can put some statistical meat on the bones to that likelihood. You can actually work out the likelihood if you know what the distribution of that random variable is. So if you know the distribution of feet size for men and women, you can actually come up with a number for the likelihood of that shoe being worn by a woman versus worn by a man.
And I'm visualizing like two normal curves, one for men, one for women. And this is at 6.5. And you could, just using a probability density function, go,
Right.
Okay, this is likely 80% of the time to be a woman's shoe and 37% of the time being a man's shoe. And you could read it right off the chart, basically.
Yeah. And what that tells you is it's still possible for that shoe to be worn by a man, even though you might think it's unlikely. That's why the concept of likelihood is quite powerful. It doesn't really rule anything out. It just talks about what is a likely parameter that described what we saw. And so the same goes with MTTF. However, there is one assumption, and that starts with, if you assume that the things you are testing all have a constant hazard rate, which is rarer than dodos these days.
Yeah.
But if you assume it has a constant hazard rate, then the time to failure is modeled by this thing called the exponential distribution. And there's also some other smart dudes and dudettes have worked out, hey, if we add a bunch of exponential random variables together, say 10 of them, then the sum of those 10 random variables is itself another random variable. And some smart dudes and dudettes have come up with another distribution to describe the random nature of 10 exponential random variables added together. And that's the gamma distribution. So this gamma distribution tells you, if you have to wait until 10 of these things fail, what is the likelihood of those 10 things, the 10th one of those things failing at this point in time or that point in time.
Okay.
And you can use that to sort of essentially mimic tests. I mean, when you test a number of things that have a constant hazard rate, essentially the gamma distribution describes the total test time, the total time it takes for 10 of those things to fail. So the gamma distribution is used to describe what our total test duration would be if we tested 10 things that had a constant hazard rate. How does the chi-square distribution get involved? Well, you use the underlying probability distribution to derive the likelihood in the same way we said, okay, it's 80% likely to be a woman's shoe, it's 20% likely to be a man's shoe.
Mm-hmm.
You have to use those bell curves that describe the distribution of shoe sizes for both male and female to get that number. Same with the gamma distribution. You use a gamma distribution to generate the confidence bounds. And it just so happens that the chi-square distribution is a particular case of the gamma distribution where you divide the number of random variables you're adding by 2 to give the degrees of freedom, and you essentially hold the second parameter constant. And the reason why we do that is because that has allowed people in the past to publish chi-squared random variable tables with just a single parameter that allows you to calculate the upper and lower confidence bounds manually, old school in textbooks,
Yeah.
on the MTTF, because it's a special case of the gamma distribution. And by manipulating it in a particular way, you only have to deal with one parameter. And so that's pretty much it. It's just the likelihood of seeing 10 or however many things you're testing fail, assuming a constant hazard rate. The gamma distribution then sort of collapses to a chi-squared distribution, and that's upon which is where you get your likelihood function for those confidence bounds come from. That might not be the best explanation, but that's the path you get.
Well, I always wondered what a gamma distribution was for. I knew it came from somewhere.
Yeah.
Now I don't like it. that constant hazard rate is, but is it the same basic process if I'm doing a mean value of something from a normal distribution? But I think if you pull a bunch of normals together, you get a normal distribution again, and you can then calculate the bounds. And for a Weibull distribution, I don't know what I've drawn a complete blank on what distribution is used for the confidence bounds. I think it's chi-squared, but I'm not sure.
No, it's not. No, it's not. It's often the chi-square distribution is used to approximate it, but no, it's for the normal distribution. If you're adding lots of normal random variables together, and then you're collapsing it to find the mean, et cetera, that's the student's t distribution to give you the confidence bounds.
Oh, okay, yep. So it's close to it, but not because you're doing a sample.
Right, and the student's t distribution sort of looks more and more like the bell curve normal distribution as you get more and more things testing.
Right.
But so you have these equations for confidence bounds on the mean for different distributions based on their shape. So if you have a constant hazard rate, it's a gamma / chi-squared. If you have a bell curve, it's a student's t. And unfortunately, there is no such distribution for the mean of a Weibull distribution.
Well, that's okay. We're not going to use the Weibull anyway. We're not going to use the mean value of it anyway. We shouldn't. And I know that it gets into really awful mathematics when you're calculating it using the matrix algebra and doing all this other weird stuff to come up with these things. But the basic principle is what's the likelihood that you're going to be 2 standard deviation away from whatever parameter you're estimating.
Right.
It's the basic idea. What's gamma used for otherwise? Because I mean, like the mean or the normal distribution is a collection of additive variables or random events, right? It could be a little taller, a little shorter. Your foot's you've been walking all day, so your shoe size is a little bigger today, and or your diet and your backup. All these things add to get a normal distribution. Um, the extreme value family of distributions, which I think the Weibull is a member of, if I remember right,
Yep,
is
it is.
kind of you have a whole bunch of things that can happen. Say that shoe could fail because the stitching comes out, or the sole wears away, or the laces come undone. All the different ways it can fail are all competing with each other, and it's whichever one happens first is the number that we're going to go forward with. I mean, it's competing hazards is the way I think of it for an extreme value. It's whatever that one that wins the race is the first. It doesn't mean the other things aren't going to happen. It's just that they're censored because it failed for some other reason first. And I think that's a characteristic of an extreme value distribution. Is that right?
Yeah, that's true. And so, in a way, the gamma distribution, it really isn't an extreme value distribution, but it sort of is in a way. One's the
Yeah.
last thing that's going to fail. Um, it's actually got a lot of utility in the natural world. For example,
Oh, we never
um,
deal with that.
yeah, well, I mean, if you think, I'm going to use a very, I suppose, flippant example, but maybe one you can relate to. If you're standing next to a road and you want to, for whatever reason, you need to understand how long it's going to take before you see 10 cars drive past you. Now, the time or distance between subsequent cars you would expect to be exponentially distributed because it's not, if they're carrying at a relatively constant rate, and the rate of occurrence of cars driving past you doesn't change. It's not affected by how when the previous car drove past or when the previous car, well, the next car's going to drive past after that,
Mhm.
then that assumption that the time between subsequent cars is exponentially distributed is a valid one. If you had to, model the time it takes for a total of 10 cars to drive past, well, that's where the gamma distribution comes. Very handy. And so there's lots of applications, including the natural world. I think cell division is one of those things where cells often divide in a very exponential way, and for it have 10 generations of cell division is quite literally 10 exponential distributions, things like that.
Mhm.
But there's not a lot in terms of reliability applications. However, if you like for the gamma distribution, I'm always using the number 10. The gamma distribution, you can insert as a parameter the number of exponential random variables you're adding. So it could be 1, 2, 10, 100.
Mhm.
Um, the higher that number becomes, the closer to the bell curve it comes. In fact, the gamma distribution collapses to the bell curve once you add an incredible number of random variables together. So there is some, I don't know, what's the word I'm looking for? Family history.
Yeah, I'm thinking of, I think it was, there's a book I saw that had like a not a flow chart, a mind map basically of all the families.
Yeah.
And there's, this one's a special case of that, and this one's a variant of that, and, on and on and on.
Mhm.
And it must have had 50 different name distributions in it. Um, so it's worth taking a gander at. But anyway, back to the original question is that I think he explained it enough that even I understood it. So I'll have to
Okay. Okay.
see how that goes. But the but understanding the background of the distributions actually is a useful thing. It's
Mhm.
why these things are related and where they come from and so on. And I know I've seen it. I know I've used it. The limited knowledge I have of all these things, but it even applies to confidence bounds. Imagine that.
Absolutely.
Cool.
There you go.
Well, I'll have to update my answer over to the person that asked this question and send them to you, send them to the podcast.
Absolutely. I mean, you can equally validly use a gamma distribution to find confidence bounds in the mean. It's just, like I said, it collapses the chi-square distribution, which only has a smaller number of parameters, which makes it a lot easier to use those old school tables for in the back of textbooks. And that's the only reason we use it. And to this
Yep.
day, there's no other reason why you could,
Use
I
it in
could show you the,
Excel and yeah, you could do it in
yeah,
Excel or any other package basically. But
but you could use the gamma distribution in Excel these days, but because it's just a hangover from how we had to use to do it
mhm.
in back in the olden days, which is fair enough. It still works if you make that horrific assumption.
Yeah, I think I have another no MTBF article in the works now. We'll have to talk about that.
Fair enough.
All right, cool. Well, that was a question that we got.
It's a good question, actually.
Yeah, no, I thought it was. Yeah, and I knew you would have some insights to this, and because that's what you do in your spare time, is think about this stuff. It definitely does.
Yep.
If you've got a question that you suspect Chris would be a great answer, provide a really useful answer about women's shoes and the likelihood of finding one on the road or other random events, let us know. Head over to accendoreliability.com/go/SOR, and you can find a couple of ways to get in touch with us there, including leaving us a voicemail, basically. You can get a hold of Chris or I, the other host of the show, through LinkedIn or our About pages on the site. So plenty of ways for you to get your question over to us, and we sincerely look forward to them. So with that, Chris, I'm going to I'll have to take a look at what distribution is the duration of our podcast, if that falls under any particular one.
My guess would be the bell curve.
Yeah, that would be my guess too. But, I don't think we've done too many of them that had negative time, though.
And actually, no, I'll take it back. My guess would be the log normal distribution, which would look pretty much like a bell-shaped cluster around 24 minutes. But yeah, the odd one which extends way out to the right. So I'll go log normal distribution. But you can do that in your spare time. How's that?
All right. That sounds good. I'll send it to you for check. Make sure I'm doing it right. All right, Chris. All right. Talk to you soon.
Cheers, Fred. Always a pleasure.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.